set AFCL, get AFCL. Okay, so where do you store that data? Where do you store that potentially massive amount of access specifications? Never mind that using these ACLs too much becomes extremely confusing and you end up in a total, chaos of permissions. So you need to be very careful not to overuse those. But even so, where do you store them? So then one choice was to attach a second inode to a file just to store these. Or in Windows, again, I'm not sure about this, but they may use another stream of the same file to store this stuff. In NTFS, I mean when I say Windows. But you cannot really have a file that has two inodes with data. Yet, I don't think you need it. The inode can cover so much space that you can fill a whole hard drive with just one inode. So you should be fine on that. Water Addict, if you have further questions, just go ahead. Pizza? Yeah, not yet. Half hour later. Now, let's see, where am I going with this? Okay, I'm heading towards the links to actually help you understand what those are, but I would like to show you two more things before I get there. Let's have a look at the hierarchy of directories and what it looks like and what it actually contains. So this is one diagram. So we're looking here at the hierarchy of directories. Yeah, one I know. Well, anything is a lot to say, but yeah, I don't think you can make a file larger than the inode that you have on disk. And if you do, you're gonna run out of space on your disk anyway. Yeah, it should be good enough. But you can calculate this. You can get the details of your disk. You can find the block size. You can find the address size. You can find how many simple indirections, direct pointers an inode has, and you can calculate the maximum file size for your file system as it is configured, and you'll figure out it goes to petabytes, not terabytes, petabytes. So yeah, you should be good. Now, if you look at the directory hierarchy, let's see here we start with the root slash, right? And then we have subfolders A, B, C. No, C is a file. A, B, D, E, right? Okay, I'm going to take a break from this because WaterEdic is touching on something. Maybe this is why FAT can have files over 4 gigabytes. That's exactly why. However, if you go to FAT, the old FAT, right, the first one, I think it couldn't take more than 2 gigabytes. And then FAT 32 goes over 4, and then I think they have an extension they could go larger. But this was the limit. You couldn't address more blocks than that. FAT 32 increased, so FAT 16 couldn't do more than 2 gigabytes, I guess. I'm not really sure. FAT 32 couldn't do more than 4 gigabytes, and they keep extending. The inode can take a whole lot more. Now let's come back to this diagram. So a directory will have a list of its children, and it will also have two special entries, which are actually links. The dot, which is a link to itself, and the double dot, which is a link to the parent. The root directory will not have a parent, so there is nothing like that. Then each entry in the directory will point to either a directory or a file. The circles are files here. And you can have in a directory an entry, which is name and inode number. And inode number, you can have it be the same as the inode number of a file. And that's where you get the symbolic link. Since the directory entry is name inode ID, you can create another entry, just like this somewhere else in another directory that uses whatever name you want, but uses the same inode ID. And that's actually an alias for the same inode. It's another name for the same inode. And since the inode is the entry point of the file, you have a link. It's called symbolic. You'll see why. You'll see what the hard link is. And you can use it as if it were the file or directory itself. So this is a symbolic link that you see right here. This G is a symbolic link. Now, the next thing I need to talk about is mounting, but I have an off-topic question from Close here. Close here. Where can we see our lab and practical grades? Yeah, this will happen hopefully in the weekend. There is a lot more stuff that I have to take care before that, but you will know your grades. You will be announced by email. um, all right. The next aspect is about mounting. This is again something that you do fairly often. Basically, if you put a USB stick in your system, mounting will take place right away. So mounting actually is associating, sort of connecting a file system to your current file system. Now in Windows, when you do that, you simply get assigned another drive for that volume, right? You plug in the stick and it shows us as drive F. In Linux, you don't have these drives. Everything gets mounted to folders. So when you come up with this USB stick, or you come in with a CD-ROM, or even mounting some remote file system, you have to put this in a directory. By the way, Windows supports that too. Instead of mapping to a drive, you can map to directory. So here is how this would look like. You have your file system here in top left, and you have a directory B. And you have another file system on the top right, which is, let's say, your USB stick. When you plug this in, the content of your USB stick will be mounted into B, and your final, the resulting structure will be like this: B containing. All right. B is not necessarily empty. B doesn't need to be empty, but if you mount on it something, its content will be hidden. You're not going to be able to access it because you're going to access whatever you mounted. When you unmount, you'll find again the content of B. Uh, head Headshot Spy is suggesting /mnt, which is exactly where the Windows subsystem Linux mounts your Windows drive. The Windows drive is NTFS. Linux has drivers for that, and it simply mounts the Windows drives to directories in /mnt. And now you can access it as if it was your own. However, it's not your own, and you've seen limitations when you work on the Windows disk from Linux. Okay, let's see if there is anything else to say. Yeah, mounting is really nice because you have a consistent structure in your file system. You don't have these drives which are somehow off, um, keep things separate. However, um, it makes it a little annoying because you plug in a USB stick and you don't know if it was mounted, and if it was, where it was mounted. In Windows, it's a little more obvious because it comes up as a drive and you can find it. In Linux, you have to figure out how is it set up and where you get to mount it, especially if you're using a command line version of Linux where you don't get any icons popping up. Then you need to know your way around sometimes to find where it got mounted. All right, so this is the mounting. Now let's go to the final piece for today, and namely this diagram. There is a little to go till we get to it. This one. So in this diagram, I'm gonna try to help you understand how these files that open by process and symbolic links and hard links work. Yeah, Berzent, chmod not working properly. If you're on the Windows drive, which is normal because Windows has a completely different style of permissions, chmod makes no sense for it. That's why FAT32 is so popular. No permissions, no trouble. It will work anywhere. Okay, so let's look at this diagram. Okay, Psych Irelia gives you a clue of how to find out what was mounted. You can also use the mount command to find the same thing, but if it is not mounted automatically, then you need to figure out your device and mount it yourself, and that's a little more work. Okay, this diagram. On the left side, we have processes which open files. So within a process, a file will basically be identified by a file descriptor, stuff that is returned by open. So you can open from the same process the same file, or you can open from several processes the same file or different files. For instance, process A and process B open the same file L, obviously in different descriptors, each descriptor its own. So this is the first thing. Processes may open the same file many times, or many processes open the same file. So within a process or across processes, you can touch the same file. Now that file, once it's open, will be part of the system open file table, which is also accessible to processes, right? Because they have their own open file table, and you can manipulate it with DAP and DAP2. So now in the open file table, these are, if you want, the names of the files. You opened /etc/password, let's say. Okay. Now, some of these files in the file system are not necessarily regular files. As you can see, O here actually goes to the kernel. So this kind of looks like a pipe, which is also treated as a file, right? From the process's perspective. R actually goes to another operating system. So this looks like a socket. Maybe it's actually a socket through which I communicate, or maybe uh, I open a local file, which is actually a remote file system mounted to mine. So again, is not necessarily a regular file. However, some of these files are actual files and point to our inodes. So you can see that M and N point to the same inode, right? In the inode table, this is that part of the disk. So what we learn from here is that either M or N, or maybe both, are symbolic links towards the same inode. This is what the symbolic links look like. You can access the same inode through its original file or through a link, or maybe both of these are symbolic links and the actual file path was not really open. And then the inodes point to data blocks. Now, the inode has the structure, but what we symbolize here in this diagram is all the data blocks pointed to by an inode. So what we're looking at here is weird if you check U and W. They both point to the same blocks of data, two different inodes pointing to the same blocks of data. So this is the hard link. So symbolic link is another name for the inode. Hard link is another inode for the same data. Now hard links are not really you can only the root can create them. They're not very common. One reason to use them is to save disk space. If you have large files with the same content and you know they don't change, then you can delete and keep just one and create hard links to them. And then obviously these hard links will have different permissions and owners as needed. Okay. If you work with Git or read about Git, if you don't, you will soon. Git is relying on hard links to reduce the repository size if you so choose, but you would need to have a really large repository to do that. So hard links are actually indistinguishable from a file because they use a separate inode. So if you really want to delete a file, if that file has hard links, you'd have to delete all the hard links to the file. Otherwise, it's not going to delete it, right? In a way, the idea is similar to the counted reference counted pointers that you have in C++. You say delete, but only the last one will actually release the data. Uh, also, because a hard link is actually another inode for the same data, you cannot create hard links across partitions. Symbolic links, you don't worry about it, because symbolic links are just name and inode number, and they can go across partitions. But because hard links need to create another inode, they cannot really have it go to another partition simply because, and okay, simply because an inode lives here and points here. So this is a Linux partition or drive if you want, but partition will be. So hard links can only go to the same partition. Symbolic links can go across. Let me see if there is anything else I want to say about this part. Uh, yeah, hard links are a little tricky because they will give you trouble figuring out how much space you have left on your disk. If you calculate your free disk space just adding up the size of the files, you're gonna, count twice or more the hard links, which will actually not occupy more space, but they will appear as files of the same size. So when you look at the disk space, you may not really rely on the file sizes. You may need to figure out what they are, and if they're hard links, then you need to count them only twice. All right. So with this, I would say I'm done with the uh, part with the files, with what we would do with the file system, and I mixed this with the actual Linux file system. But next lecture, I will go in a few other file system structures, and then we'll do a review of what we've gone through this semester, and I'll give you the list of things that I require for the written exam, and then we'll be done. Now, if you have questions about this material, this would be the time to ask them. I'll stay a few more minutes. If not, I'll stop here. Yes, they are posted on Piazza. You actually were supposed to read them before the class, which I guess you didn't. It's right in the lecture announcement. I will clarify this present in next lecture. I will tell you exactly what I'm expected to know. Some of these things I skipped over and I told you to read them, but there are not so many. So more or less what I've told you during the lecture is what I expect you to understand and to know. But we'll cover this next week. All right then. It looks like there are no more questions. Everybody, have a great day. We'll hear each other next week. Good luck with the exams. And yeah, that's it. Bye, everybody.